Hello again to the graph course, theory, application, algorithm, and implementation. So we have reached the course, the chapter distance in network. So this is the before last chapter. So in this we will talk about distances in network. So in the last chapter we have introduced what we mean by network. So it's a directed graph, and we have potential weights associated to that graph. So we have weight associated to the directed arc or the arc UV. So for example, so why we do care about networks and distances in networks? So whenever we are analyzing, for example, transportation or telecommunication, or for example, operation research problems, so digraphs, they are obviously used because they are direction, and they are additional information that is needed. So besides the direction of the arc, so we append the weights. So for example, this information could be the traffic, the road, the cable, for example. So how much traffic it's currently carrying. So in this situations, obviously, so we are slightly interested in a more complex structure, which is called a network, and how to model this problem. So we need to calculate the shortest distance or passes between a source and a destination, and this is the outline of our chapter today. So we'll be covering in the first part the single source shortest passes. So we need to calculate the shortest path from a single source, so it's a single source, to the all other vertices. So we will talk about the SSSP problem in unweighted graph. So whenever we have just arcs without weights, and then when we have a positive weighted graph, so we will apply Dijkstra algorithm, and whenever we have a negative weight and a potential negative weight cycle, obviously we will implement and we will run Bellman-Ford algorithm. Then we will move to the more generic problem, which is the APSP, the all-path shortest path problem. So we are calculating the shortest path between any two vertices. So as if we are running these algorithms again from each vertex. However, we have different algorithms, namely the Floyd Warshall's algorithm, and then we'll apply Warshall's algorithm to calculate the transitive closure. So we'll talk about that whenever we reach that part. So let's start with the first part, which is about the single source shortest passes, SSSP. So whenever we have a weighted graph, obviously, so we have a digraph and it's weighted, so the edges are directed, so we call them arc. So we pick a starting vertex S, and we need to calculate the shortest path from S to every other vertices of G. So for example, if I have S 1, 2, 3, for example, I need to calculate the shortest path from S to 2, from S to 1, and from S to 3. So this is the SSSP problem. So the problem is called the single source shortest path problem, SSSP, on a weighted graph. So there are efficient algorithms to solve this problem. So if the graph is unweighted, so for example, if there is no weights here, so we assume that it's 1, so we can apply the BFS algorithm. So we'll see it in a while. Otherwise, if there are weights here, BFS can't work, so we can either apply Dijkstra's algorithms or Bellman-Ford algorithm. So this is our intention here. So we'll be covering those three ways. So SSSP on unweighted graph. So since BFS, it will visit vertices on a graph layer by layer. So for example, if I am here 1, 2, and then 3. So we know that first in the queue we'll have S, and then 1, 2, and then I will have 3. So as if I'm visiting the vertices layer by layer. So the distance between S and 1 is equal to 1, between S and 2 is equal to 1 also, and the distance between S and 3 is equal to 2 because it's at level 2. So the BFS will visit vertices of a graph layer by layer from a source vertex. So obviously it will turn BFS into a normal choice or natural choice to solve the SSSP problem on unweighted graph. So obviously in an unweighted graph, the distance between any two neighboring vertices connected with an edge is simply 1 unit. So every one edge is counted as 1 unit. So therefore the layer count of a vertex is precisely the shortest path length from the source to that vertex. So as we have seen in the example. So obviously we'll not be interested in unweighted graphs because we were talking about a network. So we'll be moving to SSSP unweighted graph. So let's consider that we have a graph where we have two vertices or any number of vertices, and we associate a weight for that vertex. So it could be, so we call it a distance here because we are talking about a distance. So how we can find the best route from one vertex to another? So how can we find that? So if we will use BFS, so for example, if I will start from S, the same example 1, 2, and then 3. For example, let's suppose I have 2 here, I have 3 here, and then I have 1, and then I have, let's say here 4, and here I have 1. So in BFS, I will say that I have here 2, so this is not a good example. Let's suppose I want to go, I will go from 4, and then I will go to 5. So even if I will count BFS, so for example here I have, let's say I have here 1, and then 1 here, and then 1. So let's say here we have 3. So in terms of BFS, I have here 2 edges, 2 arcs, so the distance is 2. However, here is distance is 2. However, the distance, if I go from S2, 4, and then 3, the distance is equal to 3 arcs. But in terms of weights, the first pass, S1, 3, is equal to 2 plus 4 is equal to 6. The second one, S2, 3, is equal to 3 plus 1 is equal to 4. However, if I go S2, 4, 1, is equal to 3. So this pass is the shortest pass in terms of weights, but it is not the shortest pass in terms of BFS. So obviously whenever we have a weighted graph and we need to minimize or to count the shortest pass, BFS, obviously it's not the best choice. So in order to solve that, we have two algorithms. The first one is Dijkstra's algorithm. So the algorithm, it will share some similarities obviously with BFS and Prim's algorithm. However, whenever we have a vertex V, so V will receive a temporary labeling. So we'll see that now in the animation and in the algorithm. So we'll be calculating a distance, and the distance it will be just like a label, and it will be updated whenever we have a smaller distance that we can find. So we will start from a starting vertex, and the target vertex is the vertex whose distance from the root we are trying to determine. So this is what we call the target vertex. So obviously we'll be using the neighborhood, the adjacency list of a vertex V. So Dijkstra's algorithms, it will uses a priority queue. So we have already covered that in the first chapter in C++ for graphs. However, let us remind you of what is a priority queue. So a priority queue, it contains a queue, so it's a queue. So a queue, it means there's an order, but we have a priority. So it's like a queue where the order in which data arrives is important. So data comes with a priority. So we have the vertex and otherwise, and we have something with it. So we'll see that with the vertex, I will append the distance, and we'll see that. So data is enqueued based on the priority. So for example, if I have a woman here, and then I have a couple, so obviously they will be aligned in the same way, and then the first one, so the front element will be dequeued, and then I have another woman, and if, for example, I have an old lady, obviously I will let her stand in front of the line. So this is the idea of a priority queue. So we have a queue, and whenever we have people with a priority, I will pass them out. So in our case, so we have vertices, and whenever we have a vertex with a small distance, I will make it pass first. If this, for example, this vertex U is of distance 4 and this W is of distance 6, for example, and if this old lady with distance 3 will come, I will place it in front of both these. So let's see the Dijkstra's algorithm. So in order to solve the SSSP problem on weighted graph, we will create an empty priority queue. So at first we have an empty, and all distances would be equal to -1. So we have a distance list, and we have a parent list, because I need at the end to find the path. So I need a parent list, so from where I came, in order to retrieve the path. So we will place the root priority to 0. So the starting vertex, I will place it, so I will say that its priority is equal to 0, and I will enqueue it into the queue. So if I will loop over the queue, obviously, so it's like BFS, as I have said. So we loop over the queue. So if the queue is empty, so obviously I have finished. Otherwise, I will remove the front element, and then I will try to loop over its adjacent vertices. So for example, if I have S here, 1, 2, for example 2, 3, I have S equal to 0. I will make it more difficult here. Let's say I have 5 here. So I need to append first, this is the first neighborhood, 1 of priority, so let's call it AB, it's more convenient, A of priority 5, and then I need to append B of priority 3. But since we are using a priority queue, B3, it will come here. So in the queue, in the priority queue, I will have S0, which is removed now. I will have B3 because it's more priority than A5. So this is it. So if the distance of W is -1, so the distance of A and B is -1 since they are not visited yet. So the distance of W is greater than the distance of V plus W, or, so we'll see that in the animation. I will update the distance. So the distance here is -1. The distance now is equal to 5 and it's equal to 3. Why? Because the distance of A is equal to the distance of S, which is equal to 0, plus the weight of the R. So it's equal to 0 plus 5. So now the distance of A is equal to 5. And then I will enqueue the W, so the neighboring vertices, and the priority is of distance, and obviously I need to update the parent list. So this is the algorithm, so it's more convenient to do it on an example. So before that, so Dijkstra's algorithm applies to both directed and undirected. You need to know that. So it applies onto directed plus undirected. So in order to do the directed one, you need to duplicate obviously the edges and to make it on both ways. So in either case, there are generally obviously weights on the edges. However, if there are no such weights, we initially define them to be 1. So we can either apply Dijkstra's on unweighted graph and consider the arcs as weighted by 1. So the main difference here for directed weighted graphs is just the adjacency list. Obviously, for each vertex V correspond just the vertices that V is adjacent to, not those V is adjacent from. So let's do our example. So we have here our networks, and we need to use Dijkstra's algorithm to find the distance from R to T. So first we need to calculate or to just list the neighboring vertices in order not to forget any vertex. So we have here the neighboring of each vertex. So A, for example, here is A, it has 2 outgoing edges, so we have D and E. So we have D of distance 6, so we append here the 6 because it's more convenient for us to do that. Obviously, I will be using a priority queue, so this is our priority queue, and we have 3 lists, which are vertex, distance, and parent. So those are the vertices. The distance at the beginning are all -1, and we need to start. So they are telling us that I need to start from R to T, so obviously our starting vertex is R. So I will enqueue in the priority queue the vertex R with distance 0. So we need to pay that. And then I need to loop over its adjacent vertices, which are here. So I need to check. So I will do what? I will check here. I will do 0 plus 5. So A can be reached from R using 4. So I will look here. -1, it means the distance is not reachable yet. So I can update that distance. So I will say, I will enqueue first A of 4. Okay, I will enqueue A of 4. The distance is 4, and the parent, I'm coming from R, and the parent is R. Then I will move to B. So B, it's equal to 0 plus 1, because I'm coming from R. So 1, we have here -1, so I can update that because this is the first discovery of B. So I will enqueue B of 1, I will update the distance of 1, and I will say that I will come from R. Then I have C. I'm coming from R, so R, C, 0 plus 3, 3. So it should be in between. So in the animation, I've done it directly. So I have a 3, and I'm coming from R, and I'm enqueuing in the priority queue, so it will come here. Even if I'm looping differently, but it will be like this in the priority queue. Then I will dequeue B of 1, so obviously because I'm looping over the priority queue. So I'm dequeuing B of 1. Now I'm looping over the adjacency vertex of B. So I have A here. I have 1 plus 2 is equal to 3. I will look here. So if I reach A from B, it's better than reaching A from R. So this is very obvious because R to A, it will cost me 4. However, R to B, it will cost me 3. So obviously here, B, so I'm looping over A, so 2 plus 1 is equal to 3. I will update that. So I will update here and update here. So I will update A of 3 and I will say the distance is equal to 3 and I'm coming to B. So as you can see here, I will go back a bit in the animation. So it was A4 and now A3. It will remain in its place because we have the same priority and we're just updating the priority. If it's equal to 2, it will move to the front. So we have looped over A, now we have E. So E, so we have 1 plus 3 is equal to 4. 4, obviously it's minus 1 here, so I can enqueue it here directly and I'm coming from B. Now I'm dequeuing C. So in C, I have just T. So T is not visited yet. So I will calculate 5 plus 3 is equal to 8. I will enqueue it in the queue and I'm coming from C. Now I'm dequeuing A. So in A I have D. So D is not visited yet. So A is equal to 3. 3 plus 6 is equal to 9. So D equal 9, D 9, and I'm coming from A. We have E, but I'm coming from 3. 3 plus 1 is equal to 4. So there's no need to change it because this is the same distance. So we don't change it. So we have finished A. Now let's move to E. So I'm dequeuing E. I have E, which of distance 4. And from E I can reach D by an incrementing it plus 1. So 4 plus 1 is equal to 5. So it's much more better than 9. So look well here. I will update 5. It will be D of 5. What I will do? So it will move because we are in a priority queue. So now it's more priority to deal with D. Then I need to modify obviously the distance and parent of D. Now it's turn. So E, let's see if it's finished. No, because we have T. So T, 4 plus 6 is equal to 10. So obviously we have 8 here. So 8, it's more better than 10. So we drop it. We don't take it into consideration. We have finished E. So let's move to D. In D, I have the distance equal to 5 and the neighboring vertex is just 2. 5 plus 2 is equal to 7 and we have here 8. So it's better to pass by D. So I will say here 7, 7, and I'm coming from D. So we have finished D. We still have T. T, there's no neighboring vertex, and we have finished our Dijkstra's algorithm. Now we need to find the path. So we need to find the path distance from R to T. So this is T. So in order to reach T, I need to pass by D. So this is what we said. In order to reach D, so now this is our target, I need to pass by E. So this is our path. In order to reach E, I need to go by B. And in order to reach B, I need to go by R. So this is our path. So we make it in backward in order to know the distance. So the distance between R and T is equal 1 plus 3 plus, I don't know, plus 2, and we have the solution. So this is the shortest path between R and T. So I will tell you that Dijkstra's algorithm will find the shortest path from R to any other vertex. So we have here the shortest path between R and any other vertex, but we don't have, for example, the shortest path from, for example, B to R or B to D. This is not the purpose of Dijkstra. So we will see that in the Floyd Warshall algorithm, the SSSP, the all pair shortest path, the APSP problem, it will be the case. So let's do an exercise here in order to fully understand the Dijkstra's algorithm. Sorry. So we need to use the Dijkstra algorithm to find the distance from S to T. So as you have seen in the example before, in the animation, we're always trying to find the best vertex by which we can pass in order to minimize the shortest path. So in order to do that, so obviously you can do that, I don't know if you have the capacity to do that, to find the shortest path between S and T directly. I don't know. We will see that. So it's not very obvious, obviously, because it's a very complicated example. So we will do that together and try to figure out the solution. So we need to start from S and we need to reach T. So we have the vertices here. So now let me have a place for the priority queue. We have the vertex, we have the distance, and we have the parent. So the vertices are S, A, B, C, D, E, F, G, and T. So at first the distances are -1, so I will not write these because I need to erase, so I would prefer to keep it empty and just add the values. So I will start from S, so I will enqueue S of 0, obviously, and then I will loop over the queue. So I will dequeue S of 0. I have those adjacencies, so I will write them directly in order. So C of 1, so I'm coming, so here it's equal 0 plus 1, and I'm coming from S. And then I have A of 3, so it's equal 3 and coming from S. So obviously S here it's not important because it's equal to 0, so I'm S from S, this is not important. And then I have D of 3, so 3 and coming from S, and then T of 7, so I'm coming here 7 from S. So then I need to loop over the priority queue, so I'm dequeuing C, so I'm here now, and let's see, I have B2, 1 plus 2 is equal to 3, so B3, it's here. So B, I'm coming, so the distance is 3, and I'm coming from C. Then I have E, which is equal to 2, so 1 plus 2 is equal to 3. So again here I have E3, distance 3, and I'm coming from C. I have T, 7. 7 plus 1 is equal to 8. No, it's better to keep it like this. Let's move to A. So I'm here now. I have B. 3 plus 1 is equal to 4. 4, it's not good, so it's bad. I will skip it. A to C. So 3 plus 1, 4. C is equal to 1. Again, I will skip it. 3 plus 5, 8. Again, I will skip it. So there's nothing I can do with A. Then let's move to D. D, so C is equal to 1, so obviously I will skip it. E, so I have 3 plus 1, and we have E equal to 3 equal 4, so again I will skip it. G, it's a new one, so I'm in D, so 3 plus 2 is equal to 5, so it will be here. So I have 5 here, and I'm coming from D. T, 5 plus 3 is equal to 8, so again this is a good choice, so there's no need to modify it. Let's move to B now. B, we have E, so B is equal to 3. 3 plus 1, so E is equal to 3, so this is not a good choice. We have F, 3 plus 2 is equal to 5. So we have here E, we have here F of 5. So 5, and I'm coming from B. Let's continue. We have T. T, 3 plus 3 is equal to 6, so it's better. So 6, it will remain in the same place in the priority queue because there's no 6 or no smaller values. So we have here 6 in T, and I am coming from B. I will rewrite it here in order not to have any mistakes. B. So we have finished our B here. So let's move to E. We have F, 3, we have 3 plus 2, 5, so it's already 5, so there's no need to do anything. E plus G, so 3 plus 1 is equal to 4, so now it will get 4, it's better. So 4, and I'm coming from E. Then I have T, so T is 3 plus 5 is equal to 8, so this is not a good choice. So let's move to G now. G, we have T equal to 1, so G is equal to 4, T is equal to 6, so 4 plus 1 is equal to 5, so it's better to have 5. So here we have 5, and I'm coming from G, so again it will be behind F of 5 because it's a Q. So now it's turn of F. F, I have 5, 5 plus 1 is equal to 6, but however I have 5, so there's no need to change anything. And I have reached T, and we have finished. So we have found, so this is the table, so we can redraw the shortest path from S to T. So in order to reach T, I need to go by G. So G is here, so it will cost me 1. In order to reach G, I need to go by E. It will cost me 1. And then in order to reach E, I need to go by C. C is equal, so EC, so I need to go by C, so we have 2. In order to reach C, I need to go directly from S. So our path, shortest path, is S, C, E, G, T. So in Moodle, you need to write it like this: SCEGT. So it's 1, 2, 3, 4, 5. So the distance, the shortest path is distance 5. However, we have a direct path from S to T, which is equal to 7. So if I will be using BFS, for example, it will tell me, okay, this is the shortest path, but this is not the correct answer. So the correct answer is this one, is using Dijkstra's algorithm. So let's move and try to implement Dijkstra's algorithm on Moodle. So in our implementation in Dijkstra's algorithm, so as you can see, we have used, for example, the infinite sign or -1. So it's called infinite in our case. So we have the usual declaration of our adjacency vertex. We have a constant called infinite. So this is our infinite value or -1. So whenever there's no value. So we have the as a global variable the number of vertices and the source as this is the starting vertex. So we will be reading the number of vertices, number of edges, and the starting vertex, and we have the directed graph. So we need to write the function solve that just prints the SSSP problem. So we need to have this output. So we have the source 2 here, and it should calculate the shortest distance to any other vertex. So as we have seen, we need the distance list. So it's a vertex, so vertex of integer. So we call it, we have here, so it's called a distance. So we are defining it. So distance. So at first it's equal to infinite. So we have v values and all infinite, and the source, the distance of the source is equal to 0. Then we need a priority queue. So our priority queue will have two values. So we have II, it means we have a double integer. So, and we will be sorting this priority queue using the increasing distance. So this is why. So we will be using two more constructor. So you can learn these, and we will be using the greater on the pairs. So this is our priority queue. So it's called PQ. So it will store two values. So in our case, it's the vertex and the distance, but we are placing in the priority queue, so the order based on the distance on the second value. So we are pushing into the priority queue the first pair. So we have the vertex, the distance 0, and the vertex is S. So then we will be looping over the priority queue. So as long as our priority queue is not empty, I will try to dequeue one element empty and do the algorithm as we have done. So we have the first one is front, so it's double integer, it's a pair of integer. So pq dot top, and then obviously directly we do a pop. We need to remove, so it's not poo, it's pop. We remove this one. So as I remind you, so the first one, so the element, so let's hear front dot first is the distance, and the first dot second is the vertex. So let's do that directly. So in the D is the distance is called, so front dot first, and we have, for example, the vertex u is equal to front dot second. So just not to manipulate all these. So if, for example, we'll do that, so if the distance is greater than distance of u, so if the distance I'm reaching here, so in the animation, if the distance is greater than the distance of u, for example, let me go back to one of the example. So whenever we reach, for example, let's say here 3, I don't, just an example, 3 plus 6 is equal to 9. So 9 obviously is greater than 5, so there is no need to continue and check D because it's already bigger than that. So if D is greater than the distance of U, so we continue. So there is no need to continue and checking the remaining of this code. Continue. So otherwise, I need to loop over the adjacency vertex. So for in j equal to 0, j less than size, so j less than casting, and let's pick adjacency list of u dot size j plus plus. So I'm looping over the adjacency vertices. So the adjacency vertex also is a directed pair, so I need to have here v, so it's equal to adjacency list of u of j. So, and again here we have first and second. So here we are calculating. So if the distance of u, so distance of u is the original distance. So we know that if you are dealing with b, so we calculate 1 plus 2, 1 plus 3. So if the distance of u plus v dot second is less than distance of v dot first, right? So I can update here the distance. So I will relax the operation. So distance of v of first would be equal to distance of u plus v of second. So this is a good choice. And obviously I need to enqueue in the priority queue the distance. So whenever I'm pushing in the priority queue, even if the element is there, the priority will change and it will move forward if it's the case. So distance, I will enqueue the distance of v dot first. So this is the updated distance, and the element is v dot first, obviously. And this is it. So this is Dijkstra's algorithm. So let me, we need to print all these, so we'll do it in a while. So we have the distance, we have the priority queues, we have the pushing stuff. And then so for we have looped over the priority queue, we have the front element, we have looped over its adjacent vertices, we have calculated the distance. So if the distance is less than the new distance is less than the original distance, so it's a good choice. So I will update the distance and I will update the priority queue. So obviously, so for example here in our implementation, we didn't take into consideration the path, so I will keep that for you in order to, for example, print the path. So we need to use another list. So here after the while loop, I just need to calculate to print the distance. So I'm just printing here the distance from S to all other vertices. So for example, for int I equal to 0, I less than v, I plus plus. So I'll print f. So I will copy that from above, SSSP comma. So here we have the s, so percentage d backslash n. So all are d's, not s. So the first one is s, the second one is I, and the third one is distance of I. So let's check. So we have here, so first, not durst. So we have all the outputs which are correct. So let's continue our course. So before moving to Bellman-Ford, so it's important here to know that also we are finding the distance from S to T, as I have said. So we are finding the distance from S to all other vertices. So we can, for example, by modifying the root, we can find the distance between all pairs of vertices using Dijkstra's algorithm. So for example, if I want to find all pairs, the APSP problem, so I can launch Dijkstra's from S, then from A, B, C, T, E, F, G, and D, and then find the minimum distance. However, this is not a good option, and we will see that we will not be using Dijkstra's in order to solve this problem. So as you have seen, whenever we are talking about Dijkstra's, all these weights, they are positive. However, if some of these weights are negative, we have another algorithm, which is the Bellman-Ford algorithm. So if the graph has negative edge cost, Dijkstra does not work. Why? Because we are doing a summation, we are doing a plus, and we are doing this, we are trying to find the minimum. So in our algorithm, there's a less than. So if you remember well, so whenever we have a negative weights, obviously I will always pick the negative weight. So I will end up in a negative loop, and I will not find a pass. So maybe we'll have an example why we may have negative weights on the graph, because for example, you can model a graph, for example, for winning or losing. You can lose some money, gain some rewards and stuff like that. So we have graphs or networks with positive and negative weights. So how we will solve that? So we'll have a combination of Dijkstra's algorithm and some unweighted algorithms that will solve the problem, and this is what Bellman-Ford do. So the main idea of this algorithm is simple. So we will relax all e edges v minus 1 time. So we'll repeat the relaxing this. So we will repeat the relaxation of this edge v minus 1 time. So we'll see how we'll do that. So in Bellman-Ford algorithm, we'll be using just a normal queue. So obviously we'll have the distance. However, here our distance list is initialized to plus infinity. We have also the parent, that if you want to find the pass, if you don't want to find the pass, we can omit the parent list. So we have a Boolean list which is called in queue. It's not in queue but in the queue. It means if it's in the queue, yes or no, that state whether a vertex is in the queue. It says yes, it's in the queue, not is in the queue. So again, we will do the same way. So we have the root, which is distance equal to 0, and I will set its in queue state. So yes, it's in the queue, and I will in queue it in the queue. So I will loop over the queue. Obviously, if there's no elements in the queue, the algorithm ends. Otherwise, I will pick the front element, I will remove it, I will set in queue to false. It means that it's no more in the queue. I will loop over its adjacency vertices. So if the distance is greater than distance, so if the distance of W is greater, so we'll see that in a while. So we will update the distance, we will update the parent, and if W is not, so it's the adjacent vertex is not in the queue, I will enqueue it in the queue. So let's do that in the following example. So it's the same example, however, we have modified some of these edges or arcs and make it negative in order to understand. So this is a queue, so there's no priority. So as you can see, there's no R0, there's just R. All the distances are equal to 0. We have R, it's our source, distance equal to 0, and in queue, it means it's in the queue. So I will loop over the queue, I will remove R, and I will loop over as adjacent. So I have here A of 4. So A of 4, I have here the distance plus infinity. So 4 is more better than plus infinity. So I will say that it's 4, and I'm coming from R. Now A is in the queue, so I will set is Boolean to 1. Now I have B minus 1. So minus 1 is better than plus infinite. So minus 1, I'm coming from R, it's in the queue, and I will place B in the queue. So the same for C, you have known that. Now it's the time of A. So I will dequeue A from the queue. I have here minus 2. So A, I can reach, A, I have E1. So again, E. So it's equal, now A is out of the queue, okay? So now we have E is equal to 5. Y is equal to 5 because in order to reach E, I need to pass by A. So the distance to reach A is equal to 4. 4 plus 1 is equal to 5. So 5, I'm coming from A, and now A is in the queue, E is in the queue, and I'm placing it into the queue. So now A is finished. I will dequeue B. So B now is out of the queue. B, we have A. So B minus 1. Minus 1 plus 2. So it's equal to 1. So 1 is better than 4. So I will update 1. I'm coming from B. And now it's in the queue again. So I have A in the queue again. So B, we have still E. So E, well, it's E is 5. So B is equal minus 1. Minus 1 plus 3 is equal to 2. So 2 is better than 5. So 2. I'm coming from B. Now it's already in the queue. So there's no need to re-enqueue it because we didn't reach it yet. So let's continue. B is finished. Now is the turn. So B is finished. It's DQ. So it's now the turn of C. I will remove it from the queue. C, it has one adjacent vertex. So T over 5. So 5 is better than plus infinite. We have C. This is equal to 3. 3 plus 5 is equal to 8. So 8 here. Parent is C, and it's in the queue because I will in-queue it now. So we are C, so this is it. Now it's the term of E. E, I will remove it from the queue. E, it has a D as adjacent vertex and T. So D equal to 1. We have 2 plus 1 is equal to 3. So 3 is better than plus infinite. I'm coming from E, and now D is in the queue. We have, so D is in the queue. T is 6. So E is equal to 2. 2 plus 6 is equal to 8. So it's the same. So there's no need to modify it. Now, T, so T, there's no adjacent vertices, so we do nothing. Now it's the term of D, so D, where's D? So 3. 3 minus 2 is equal to 1, so it's already 1, so I do nothing, so I need to remove it here. Then I have D, which is equal to 3. 3 plus 2 is equal to 5, so it's good choice. So I will modify it and make it D, and I will in-queue it again. Look, so I will in-queue T again. So I will repeat T. So why we do that? So we are relaxing T. So why the purpose of doing this multiple times? Because we have found a vertex that we can, if we pass by it, we can find a shortest path. So we are retrying it. Maybe we can find a shortest path from that. So at T here, we will repeat it. So there's nothing to do, and then I will finish, and we have found the shortest path. So I want to reach T, so the same we are doing backward. In order to pass by T, I need to go by D. In order to go by D, I need to go by E. To go by E, I need to go by B. So as if we have the same, and B equal to R. So we had the same path as in the previous example. So the relaxing here, it means I need to, as if I'm retrying to pass by this vertex, I'm rechecking this vertex, because while working with this algorithm, I have found that A could be a potential to help me find a shortest path to other problems. So again, we have another example, and we need to use Bellman-Ford algorithm to find the distance. So we may find that we have here a negative cycle, so we'll see if it's the case or not. So we need to use the Bellman-Ford algorithm to find the distance from S again to T. So we have here the graph and the neighboring vertices. So I have here my Q, and we have our vertices here, vertex A, B, C, and T. We have distance, so at the beginning it's all plus infinite. We have parent, and we have the state of if it's in the in-queue or not. So we start by S, so S, it's in the queue. We will remove it, so now it's out of the queue, and I will try to work with its adjacent vertices. So here S is equal to 0, so let's place it here. Distance 0, there's no parent, and it's in the queue, and then it's out of the queue. So A of 6, so 0 plus 6 is equal to 6. So parent is S, and I will place it into the queue. Then I have B, 7, S, and I will place it into the queue. So this is S. Then I need to remove A, 0. A, we have B, C, T. So A is 6. 6 plus 8 is equal to 14. We have 7, so let's ditch it. A is equal to 6, C is equal to 5, so 11. 11, I'm coming from A, and now is in the queue. T minus 4. We have 6 minus 4 is equal to 2, so it's good point, 2, A, and now is in the queue. We have finished A, so let's move into B. B, distance is equal to 7. 7 minus 3 is equal to 4, so now is equal to 4. And I'm coming from B, but it's already in the queue, so there is no need to re-in-queue it because I didn't yet visit this vertex, so I will keep it. However, I have found a shortest way to reach C. However, I didn't yet work with C. So I'm still in B. I have finished with C. Let's say T. So B is equal to 7. 7 plus 9 is equal to 16. Is greater than 2. So obviously I will do nothing. So B here is out of the queue because I have worked with that. Now C is out of the queue. C, I have A minus 2. 4 minus 2 is equal to 2. So it's better. So 2. I'm coming from C. And now it's again in the queue because I have found the shortest way to reach A. And I'm coming from C. So C, we have just this, so we have finished, sorry. We have a T, so T, it's now T, so T is out of the queue. T, it has C and S, so T is equal to 2. 2 plus 7 equal to 9, so 9 is greater than 4, I will ditch it. 2 plus 2 is equal to 4. So 2t plus 2 is equal to 4. So obviously 0 is better than 4. We'll do nothing. So now let's do A because t is finished. A again. A we have A is equal to 2. 2 plus 8, 10. So 7 is better than 10. So A now is out of the queue. 2 plus 5 equal to 7 for C. So 4 is better. 2 plus minus 4 minus 2. So minus 2 is better. Minus 2. And I'm still coming from A. So we'll see that as if we have a cycle here because I was from A and I'm redoing that and I'm in A. And now T is in the queue. Let's repeat that. So T is minus 2. Minus 2 plus 7, which is C. So is equal to 5. So 4 is better. Minus 2 plus 2 is equal to 0. So 0 is better. Now I have finished and this is our Bellman-Ford algorithm. So let's see what's the shortest path from S to T. So in order to reach T, I need to pass. So I need to reach T, I need to pass by A. So what is A? So this is A. In order to reach A, I need to go by C. In order to reach C, I need to go by B. In order to go by B, I need to go by S. So it's S, B, C, A, T. So SB is equal to 7. BC minus 3, minus 2, minus 4. So the total is minus 2. So this is the shortest path of our Bellman-Ford algorithm. So I can reach S to T using minus 2. So 7, minus 3, minus 2, minus 4. So minus 4, minus 7, and minus 2 is equal to minus 2. So this is the Bellman-Ford algorithm. So as you can see, this is negative. And this is very obvious. So as you can see, if I go to T to S into 0, so as if I have a cycle of 0. So if I go like this, so from S to S, I can go from 0. So for example, if I had here 1, the cycle would be negative, minus 1. And we will see that in our implementation, we need to detect whenever we have a negative cycle. Because if we had here 1, obviously it's better to loop infinitely because at each time I'll be having minus 3, so I'll be having a negative value. So it's not equal to 0, it will be equal to minus 1. So as if I'm finding a shortest path, and this is a negative cycle. So this is a major problem whenever we have a negative cycle. So we need to detect negative cycle. So Bellman-Ford can be used to detect the presence of negative cycle. So as you can see, after relaxing the all edges v minus 1 time, the SSSP problem should have been solved. It means we cannot relax any more edges. So the relaxing means how many iterations we can do. So obviously at some points we cannot do more iterations, but as you have seen here, if it's equal to 1, I can continue indefinitely. So if we can still relax, or if we can still continue like this, there must be a negative cycle in the way to the graph. So let's see an example in order to understand that. So we have this simple graph ABC. We have those neighboring. I will start from A. So A distance is equal to 0, and now it's in the queue. I will dequeue it. I have B 1000. I'm coming from A, so it's in the queue. In B, I have one adjacent vertex which is equal to C, so it's equal to 1015, and I will enqueue that in the queue. So obviously we have it equal to 0. I'm not working with these. So whenever we reach C, so C is equal, it will reach here B minus 42. So minus 42, it means 1050 minus 42, it's equal to 946. Now I will enqueue B in the queue, and so on. So I will repeat that infinitely. So as there's a negative cycle, I'm writing this. We can still do this again and again. If we can still relax the distance, so the second one, it will be equal 988. So this is lower than the current value. So if we can repeat that indefinitely, it means that we have a cycle. So before going to the APSP problem, let's go to our Moodle page and try to implement Bellman-Ford algorithm. So in order to do that, so we have the same input, the same adjacency list, the infinite and stuff, and we need to calculate the SSSP for example, if the graph contains negative weights. But before that, we need to check if there's a negative cycle, yes or no. So in order to do that, obviously we will be running the Bellman-Ford, and we will see if we can still relax. We can continue with doing this, and if we can continuously update the distance, it means we have detected a cycle. So we have here the same algorithm as in Dijkstra, so I will go back and try to copy it because it's more convenient. So we have we don't have a priority queue, we have a queue. So I will just copy these and try to continue from there. So we have the distance vector. So at the first, the distance is equal to 0 of the source. So I need to repeat at most, as you have said, V times. So this is relaxing. So I can repeat each iteration V times. So we are relaxing the E edges V minus 1 times. So for int I equal to 0, I less than V minus 1, I plus plus. So this is the idea behind Bellman-Ford, just to repeat. This is the maximum time. So for int u equal to 0, u less than v, u plus plus. So we are looping. So this is just for the Bellman-Ford, so the relaxation. So I'm just the number of times each edge could be relaxed, how many times we can repeat that, and then this is the vertices. For each vertex, I'm looping over its adjacency vertices. So here we have another loop for j equal to 0, j less than int adjacency list of u dot size j plus plus. So here I have one pair, so adjacency list u of j, and I will be updating the distance as we have done earlier. So distance of v dot first is equal to the minimum of distance of v dot first and the summation, obviously. So distance of u plus v dot second. So you can record here the spanning tree if you wanted. So you need to another parent vertex. So we have so this is just the Bellman-Ford. So we need to check if we have a negative cycle. So this is why we will have a Boolean, so a negative cycle. So at first we will have it should be initialized to false, and then I will trying to repeat the Bellman-Ford. If I can do one more pass, so if I can do one more pass on this, it means that we have a negative cycle. So I will copy this. So this means one more pass, because it means if I can do that for one more time, it means that we have a negative cycle. because this is the maximum number of times, which is equal to v minus 1. So for u equal to 0, u less than v. So if for j less than adjacency, again I have the I, and here we need to test. So if the distance of v dot first is greater than the distance of u plus v dot second, so if still, it means if we can still do that, and it should be false in fact, so the negative cycle is equal to through. So if the oldest value is greater than the newest, it means that the newest is less. So it means that I can still, there's a negative cycle, and we have found the negative cycle. So I will repeat, we have here a maximum v minus 1 time, so we can do that. If we can still relax, if we can still find a minimum distance, it means we have a negative cycle. So if there's a negative cycle, let's copy this. We should print yes or no. So percentage s backslash n. So we will check. So if negative cycle is different than 0, I will print yes. Otherwise, I will print no. So after doing that, I just need to print the SSSP. So obviously, if there's no negative cycle, because if there's negative cycle, it means the values are wrong. So if negative cycle is different than 0, so it means if not negative cycle, I will do a for loop for int I equal to 0, I less than v, I plus plus, capital V, and I will print f SSSP of those vertex. So here we have percentage D backslash n. The first one is s, the second is I, and the third one is distance of I. So let's check. So here we have j and j, so in j equal to 0, and okay, so this is correct. So this is a nice algorithm. So we still have one more algorithm, which is about the all pair shortest path, which is the problem. So this is our part now. So in the all pair shortest path problem, so in some application or in some problems, we require the shortest path information from all possible sources. It means all possible vertices, not just from specific vertices. So as I have told you, we can make a vcall for of Dijkstra's algorithm, but obviously this is not a good option. So we have a better solution whenever we have a shorter graph when the number of vertices is shortest. So this is the Floyd Warshall's algorithm. So here we'll be using the adjacency matrix, not the adjacency list, and we'll be using the same way or concept as we have seen in Dijkstra's and Bellman-Ford, but this is what we call dynamic programming, because we have a two-dimensional arrays and we are updating the values in the two-dimensional arrays. So we will load the graph into an adjacency matrix called adjacency. And then we will run the following code. So it's just 3 for loops. It's as easy as that. So when it terminates, we will find an adjacency. So it will contain the shortest path distance between any two pairs. So you should pay attention that the outer loop is k. So we'll tell you in a while what does it mean k. The inner loop and the outer loop, so they are int I and j. So as you can see well here, we have just k here. So this is the same as the multiplication of adjacency. So we have 3 for loops. The outer loop is on k. All are looping from 0 to v, and the adjacency I of j is equal to the minimum of the oldest value of the adjacency, then the minimum was the adjacency ik plus the adjacency kj. So in order to understand what does it mean k and why we do that, we will have to run an example, and obviously again you will have an exercise on that in a model. So the idea behind the Floyd Warshalls is to gradually allow the usage of intermediate vertices. So if I have vertices between 0 and k, at each time, at each k, I will consider a specific number of vertices. So at first, I will consider one vertex. The second iteration, I will consider 0 and 1. It means I will consider 2 vertices. The third time, I will consider 0, 1, 2. And at the end, I will consider k. We will see that in the animation. So I will have here an example. This is our network, and we have here the adjacency matrix, adjacency ij. So at first, at k minus 1, it means I'm not considering anything. I'm just placing the values as I'm seeing it on the graph. So the distance between 0 and 0, so obviously it's 0. The distance between 0 and 1 is equal to 2. Between 0 and 2 is equal to 1. Between 0 and 3, there is no distance, because there's no direct distance, because there's no direct edge or arc between 0 and 3. So it's equal to infinite. Between 0 and 4 is equal to 3. So this is the direct. It means k equal minus 1. It means as if I'm just using the adjacency matrix. So there's no direct arc between 0 and 3. So this is k minus 1. Now, so we want to find, in our case, SP344. So it means I want to find the shortest distance between 3 and 4 by k equal to 4. What does it mean, k equal to 4? It means I will consider the vertices 0, 1, 3, 4. It means I'm considering all the graph. So in order to calculate that, so they are telling here that the eventual shortest path is equal to 3, 0, 2, and 4. So, but in order to find that, at the beginning, if you can see well, 3, 4 is equal to 5. However, we have a shortest path of 3. How we can do that? Via Floyd Warshall. So we'll be doing that by adding at each time one vertex and recalculating this graph. So now I'm considering k equal to 0. What does it mean? It means I can calculate the distances between any two vertices, but I can also pass by 0. I will just consider 0 now. So, for example, if I want to go from 3 to 4, I have 3, it's already here, but if I'm considering 0, I can take this path and it will cost me 4. So this is a better solution. So I have it here. So because we are interested in that. So when we allow k, it means vertex 0 can now be used. So sp3 of 4 is equal to sp3 of 0, 1. So it's equal 3, 0, minus 1. It means the direct path plus sp. So it means the oldest value in the adjacency list, which is equal to 4. So 4, so now it's minimum. So as you can remember, it's the minimum between adjacency of ij and the minimum of adjacency ik plus adjacency of kj. So this is it. So this is minimum. So now this is a good option, and I can update this. Obviously, I can in our code I will do that for all 0 for all the vertices. Yeah? So for example, s32 I can pass by 0. So I have 2. s32 is equal to 3. So 2 is better. So I can update that. Even if S31 can also, I can have this 3, so it's not more infinite. So I can update all this row using a 0. So I have considered k equal to 0, so all the other values, they are not changed. You can try this. In the model example, you need to recheck all these, obviously, but this is just an animation here. So all the other values, they remain the same, just those 3 values, they change whenever we consider k equal to 0. So obviously the next step is to consider k equal to 1. So what does it mean, k equal to 1? It means I can consider both these values. So I have already k equal to 0, so I just need to consider now as if a is an intermediate vertex, and I can use it. So for example, you can check as, for example, the distance between 2, because 2 it will pass by 1, 2 and 3, for example. So 2, 3, there is no distance. However, if I want to go to 2 and 3 via 1, I have a 5. So I have here, for example, 5. Also, I have from 0 to 3. I can, so it's infinite. However, I can pass and take 6. No? So again, I can, let me erase all these. So we have 5 and 6. So in your case, you need to check this, and in the code, just the 3 for loops, it will be done automatically. So the next step is to consider k equal to 2. So what does it mean, k equal to 2? It means to consider all these 3. But we have already k equal to 1, which contains 0 and 1. So I just need to consider 2, starting from this matrix. So for k equal to 2, again, I can modify those two, so we need to check all these. I will end up here with 3 and with 2 here. And so we have found the shortest distance. So obviously we can add k equal to 3 and k equal to 4, obviously, in order to find that. So we have here, so Floyd Warshall's repeat this process for equal to 3 and k equal to 4. However, this will remain the same, and this is the final answer. So as you can see, I and j, they are here. However, k, it will move. This is the outer loop, and it will modify the values accordingly. So before implementing Floyd Warshall, there's just a notion, what is the transitive closure. So Warshall, so using his algorithm, he developed another algorithm for the transitive closure problem. So what does it mean, a transitive closure? It means given a graph, we need to determine if the vertex I is connected directly to j. It's either directly or indirectly. It means if there's a connection between I and j. So since initially adjacency A of I will contains 1 if the vertex I is directly connected to j, so this is easy, or 0. So here we will be using just a modification of this algorithm. So again, we will have the 3 loops. However, we will just do this operation to check. So either adjacency I of j is equal to 1, it means we have a direct connection, or indirectly via what we have done, we can check if there's a connection, yes or no. So we can use that in order to know if there's a direct connection. So there is no need to do BFS or BFS in order to check if there's a pass between any two vertices. You can check these, but obviously this is too consuming in terms of implementation. So let's move to our model and implement these 3 lines of code. So we have here the infinite also. We have the adjacency matrix, as we have said, because we are doing a dynamic programming stuff. So in our reading, so we are reading the number of vertices and number of edges, and then we are reading the adjacency matrix. So we have here the I, j, so the first 2 vertices, and then the weight. So before doing that, since we are using C and C++, we need to initialize to infinite all the entries in the adjacency matrix, and for those in the diagonal, we need to specify it as 0, since at the diagonal the distance between any 2 vertices is equal to 0. And we need to write the function void solve, that it will print the APSP value. So it means the all pair shortest path between all the sets of vertices. So this is very easy. Int k, so I will remind you that k is always the outer loop, k less than v, k plus plus, the inner one. So for int I equal to 0, I less than vi plus plus. For int j equal to 0, j less than v, j plus plus. And then I have here adjacency matrix of ij is equal to the minimum of adjacency matrix I of j, comma, adjacency matrix ik plus adjacency matrix kj. So this is it. And then I just need to print the adjacency matrix. So I will copy all these, and I will print the APSP is equal, so printf backslash n, comma, so the first one is I, the second one is j, sorry, and the third one is the adjacency, because the value would be in the adjacency. So here we have I, j, and then adjacency matrix of ij. And this is as easy as that. So as you can see in the APSP problem, we can also solve the shortest path, the SSSP problem, because it will be contained in the matrix. So for example, here we have the shortest path between 2 and 3 is equal to that quantity. So here we have capital V, and we have all these correct. So as you can see, the all pair shortest path. So we have here the shortest path between 2 and 2. So as if we are running Dijkstra multiple times, but this is very convenient. But you should pay attention that this won't work for big graphs, because as you can see, there's a tree loop, so the complexity will be very high. So it's better to avoid that and just use it when the graph is small. So for example, as we have seen here, maximum it will be of 200 multiple 200 vertices, or just 200 vertices. So this is it for this chapter. We still have one chapter, so if you have any questions, do not hesitate to write to me or to use the forum. And again, thanks for watching.